So when you start learning about simple harmonic motion, you start with the spring force, or the spring potential energy. Spring potential energy looks like a parabola. It's got a 1/2 times the spring stiffness times x squared. Really, the only thing you can change about this is the value of k. You can use it to make the well stronger or weaker, but either way, it's still going to be an x squared. And it's always going to give you the result that x equals a cosine of omega t. And you can shift it around left and right. You can shift it up and down if you want. But the important thing is that it always gives you a cosine. That's always the solution. But it turns out not every potential energy behaves like that, right? Some potential energies will do some pretty wild stuff over the course of space, right? So this is, some random potential energy. But what you can do using these results is if you identify a spot that's got a minimum, like say here, or even here, or here, each of those has a minimum where the potential well goes up from there. If the particle doesn't have a whole lot of energy, it's not going to be escaping into all the other little hills and valleys. And so it'll oscillate around there. And so what you can do, you can define a K, a spring stiffness, that'll allow you to take this potential energy and approximate it as 1/2 kx squared. All right, if you set this spot equal to x equals 0, define that as your equilibrium point. And that's really the true power in the simple harmonic motion stuff, is not because 1/2 kx squared shows up everywhere, but because 1/2 kx squared turns out to be a decent approximation for a lot of weird potentials out there in the universe. Now, obviously, if you get too far away from this, it's going to start to depart from that approximation, and you'll end up with an error there. But for small oscillations, it works out pretty well. But what other kind of potential energies might you run into that kind of go beyond this 1/2 kx squared? Well, the next logical stop would be to try your potential energy equal to some number times x to the 4th, right? X to the 3rd won't work because the potential energy will go up one side and then go down the other side. Obviously, the ball is going to roll off to negative infinity. You'll never see it again. But for this thing, the super spring, as I tend to call it, I think it's technically called the anharmonic oscillator. I like calling it super spring better. It looks similar to this. The difference is x to the 4th, it's always going to be sharper than x squared. No matter what combination of numbers you use in front here, x to the 4th is always going to grow faster than x squared. So it's going to be much sharper than this one. And the downside to using that, it's a lot sharper, it's a lot stronger, but the downside to using that is we cannot solve that. Right? So negative kx equals ma, I can solve to get the cosine function there. But let's see, what force would that be? That would be a negative 4ax cubed when you take the derivative of that. If you set that equal to ma, I don't know what x becomes there. And that's not just me that doesn't know that. That's the human race doesn't know that. We have not made the math to solve that differential equation yet. We can do it numerically. We'll do that numerically in just a minute. But we don't have a function that gives you that gives a name to this thing, right? And so as soon as you go beyond 1/2 kx squared, you're entering territory where you can't solve it. But the good news is I can still use the kinds of quantities we used before. I can still use amplitude and I can still use period. It just won't be mapped onto a nice cosine graph. And in particular, I'll be able to see that the period here is now going to actually depend on the amplitude we have. Remember, that canceled out up here where it doesn't depend on the amplitude, but here it is going to depend on the amplitude. Now, of course, I can get a step weirder, right? Because even though these are both unsolvable, they're at least both symmetric, right? So if I look at the equilibrium point, I'm getting the same kind of potential energy shape on one side as I do on the other side. So I could technically flip this around, still have the same potential energy. So let's take a look at an example of what an asymmetric potential might look like. So let's suppose I've got a potential energy. Let's put an epsilon out in front. That'll take care of the units because that shows me how strong the potential energy is. And let's do a couple things. Let's take 1 over x to the 12th power. Why the 12th power? You'll see why in a second. It's necessary to describe the system this is designed for. And because I want this to be a pure number, I need to put another distance up here. So xm, you're going to see in a second, is going to be the location of the equilibrium point. Okay. Then we'll subtract from that xm divided by x to the 6th. So remember, xm is a constant. X is the thing we're graphing the potential energy against. So let's graph our potential energy versus x. We're going to go pretty far out here just to get an idea of what this thing looks like. So I've really got two competing terms here, right? I've got a positive term that goes like x to the minus 12, and I've got a negative term that goes like x to the minus 6. So we got to think about the extreme ranges of this. As I get closer to x equals 0, I'm dividing by progressively smaller numbers. When you divide by a small number, you get a big number, right? So this is going to be a big number to the 12th power, and then that same big number to the 6th power. Even though they're both big numbers, big number to the 12th power wins out over big number to the 6th power. So when I get close, this term's going to win out. So when I get close to x equals 0, this thing is going to shoot up in a very steep asymptote at x equals 0, right? Because if you divide by 0, we'll get an infinity, so this thing is shooting up toward infinity here. On the other hand, if I get far away, if I get a large value of x, when you divide by a large value, you get a small number. And a small number to the 12th power is a whole lot less than a small number to the 6th power. Make no mistake, they're both going to be small. They're both going to be pretty close to 0, but this one's a whole lot closer to 0 than this one is. So in other words, over here, the 1 over x to the 6th is going to win, and it's negative 1x to the 6th, so it's curving downward. What that means is somewhere in the middle, I've got to be able to turn around, because here I'm heading downward, here I'm heading downward, so at some point, I've got to have a minimum. It turns out, if you do the math on this, that minimum is located at this xm value that we have here. And so what I've got is another minimum, just like we had on the weird potential up here. I could, in principle, do a 1/2 kx squared approximation here. Right, let's draw that a little bit better. There we go. I could, in principle, put a parabola in there. But here's the problem. This is incredibly asymmetric because this side is a whole lot sharper than this side. This side's eventually flattening out and heading to 0, right? I've got an inflection point in there somewhere. This point is going much, much steeper. It's got an asymptote. Those are things that 1/2 kx squared cannot do. So for teeny tiny oscillations, you can use the approximation, but if we really want to see how this potential energy works, we can't use that approximation anymore. And so what it also means is that my oscillation behavior is going to be different on one side versus the other side, right? On this side, it's going to return very quickly to the middle, whereas on this side, it's going to take its time falling back down to the hole. So we'll get some asymmetric behavior in x as well. But again, even though I can't solve this, because if I can't solve x to the 4th, I sure can't solve this. I can still use the concepts of amplitude and period because it's still going to oscillate. I can still use these concepts of amplitude and period. I just don't have a nice, neat equation that governs my motion like I had for simple harmonic motion.
Okay, so let's start by adjusting our restoring force. Instead of negative k times x, let's try negative k times x cubed. And technically, this should be a 4 times x cubed. It doesn't really matter what the thing is in front, so we'll just leave that there. Well, we're going to turn off for right now the damping force and the driving force. So we'll just make this a 0 for right now. I'm also going to leave out the animation because I think we can pretty much get what we need from the graphs at this point. So the only force we'll have working for us right now is the restoring force here. So let's press Control 2 to run, see what we get. Oh, whoops, I started the x at 0, excuse me. And let's give our x a starting value. Let's start it out at something small. Let's try like a quarter maybe. And so what we get, we start up at 0.25, we get pulled down this way and then back up. So it's still an oscillating function. You might almost even be able to squint and call it a cosine, but what you notice is that these regions in the middle, in between the maxes and the mins, is a little bit too straight. It's a little bit too linear compared with the nice curvy nature of a sine and cosine. You can definitely see a difference in the phase space plot, because phase space plot no longer looks like an ellipse. It now looks kind of like a medicine tablet or something. And you can see at the points where I'm getting straight along here, all right, that's where my velocity is going to be a constant. I'm getting pretty much constant velocity along here. And so this is very different than what we had before. Now, even though this isn't a proper cosine, I can still pull a frequency off of here, right? Because I can look for the repetition in the pattern, and I can see that this thing's got a period of about 7.3. So I'm going to make a note over here that we've got a period of 7.3 when we had an amplitude of 0.25. But let's see what happens if I change the amplitude drastically. Let's suppose I up this all the way to 10. So let's hit Control-2 to run. And what you notice is I've still got the same pattern, but my frequency has decreased dramatically. My frequency has decreased by about a factor of 10. So it's down to 0.7 instead of 7 point something. So when we have this super spring, we do end up with the frequency depending on the amplitude quite strongly, actually. Let's try a different restoring force. So let's get rid of our super spring here, and let's try the Lennard-Jones Force, because even though it's nice and different here, it's still symmetric, right? It's still a symmetric potential energy. This Lennard-Jones Force produces a very asymmetric potential energy. And now I have written down the initial conditions I wanted to try, just because I want to be able to make sure we get something reasonable here. So the way Lennard-Jones works is you have the depth of the potential energy, and then you have the equilibrium point. So this xm is the equilibrium point. So let's try an x value near xm. So let's try, instead of a 6, let's try a 5.9. So we're taking that, let me remind you of what this looks like. Lennard-Jones potential looks like this. So here is your xm. And so we're going to start just to the left over here. That's what our x initial is going to be in this case. All right, let's press Control-2 to run. And you notice because I'm near that minimum, my oscillations are pretty symmetric. This thing is looking pretty good here, and it's oscillating about that equilibrium value 6, right? So 6 is our new equilibrium value. But phase space plot, it looks pretty elliptic, right? It looks pretty close to what we got before. So in this case, for this small amplitude, the simple harmonic oscillator is actually a pretty decent approximation. All right, let's move out just a little bit farther. Let's try moving out to let's try moving out to 5.8. I want to be careful because this thing is so asymmetric. If I start out too high, I'll end up shooting past here. Not that that's a problem. I just want to get some oscillations first. And what you notice here, I'm starting to get a little bit of asymmetry, right? Because if I look at the peak opening up, it opens up a little bit wider than the trough does, because the force is much stronger as you get closer to 0, right? As you get farther away this way, the force gets much stronger than it does when you go out this way. And I can see that in my phase space plot because my ellipse is getting distorted. It's a little bit more egg-shaped here. You can see it's getting a little bit pointed here compared to over here. And let's go ahead and bump it all the way over to 5.5. And here we're definitely getting some asymmetry, right? Because here we are getting this nice kind of sinusoidal shape up here, but then down here it's getting much narrow. It's almost turning into a corner there. And you can see we get a very different shape for our phase space plot. This is definitely not an ellipse, right? It's definitely not symmetric going left and right. It is symmetric going positive negative of the velocity, but going left and right in the position, it is definitely not symmetric. All right, I also want to try taking this thing out far to the right, because what will happen if I take it out to the right, let's suppose I start way out here at x equals, let's say, 20. What will happen here is I won't have a lot of force at the beginning. I'm just going to slowly start to fall down, and then I'll end up shooting past here and going up the same height along this side here. So let's change this to a 20 and Control-2. So you see I start out with not a lot of change. In fact, I need to increase my maximum amount of time there. Let's change this to a 100. There we go. And so you see I start out with not a lot of change. I haven't even reached 15 until just now. And look how asymmetric this is. This is nice and broad up here. And then I get this cusp really right here. At least it looks like a cusp. It might not exactly be a cusp, but I get a very sharp turnaround here when I am trying to go up the hill as opposed to along the outside of the valley. And look at what's happened to my phase space plot. It's not even egg-shaped anymore. right? It's trumpet shaped almost. It definitely looks like I got a cusp right here. So yeah, so the Lennard-Jones Force gives you this really interesting stuff going on here. All right, let's clear this out. Let's see what happens when we add in our damping force and driving force. I'm just going to add those in like we had them before. We'll probably need to make some adjustments to those. Let's just add those in like we had before to our Lennard-Jones Force here. Okay, so you see my driving force, it allows me to escape, and so I am traveling out along this way. Oh, the velocity. Oh, yeah. This is my phase space plot. So that's probably a little bit too much amplitude there on the driving force. Let's try making that a small number. Let's try making that a 0.1. Let's see if we can still get some oscillations out of this thing. Okay, so we're getting oscillation like we had before. Okay, so where we start to get our bugle shape, and then it ends up curving around this way. And this is interesting because I'm getting a different radius of this interesting shape here each time. Here's my position versus time graph. So you can see it's kind of leveling out. So I can kind of see there's kind of like some long-term behavior inside this little shell here. That's pretty cool. Let's see what happens if we take this and start it over to the right instead. So we started it, let's go with 5.8 like we had before. Okay, we're getting kind of the same thing we had before because it's still basically behaving like a harmonic oscillator. We are spiraling inward though because of that damping force. That's pretty interesting. Let's try one more thing. Let's put this back out to 20. I think I like that better. Let's try changing this frequency. Let's see what happens if we double the frequency on the driving force. I'm pretty sure I'll get pretty much the same thing because the frequency is what's changing these internal wiggles. Yeah, and then I pretty much get the same little sideways gumdrop shape here, which is kind of cool. All right, let's really change the driving frequency. Let's up that by a factor of 10 now. It seems like that smooths out a lot easier. I guess so, because these wiggles are getting less consequential. Yeah, I don't think we're going to pick up that much of a frequency on this. What we could do would be to try to match that frequency with kind of the natural frequency that's going on here. Well, I guess it's not really a natural frequency. One natural frequency. We could try making that, like, let's say this goes from 76 to 78, 78 to 80. Yeah, let's try making that frequency. Let's see if the period is 2, then the frequency is a half. Let's see what happens if we try to stumble on that resonant frequency there. Oh, that's okay. It's still shaping out to what it was before. Okay, yeah, we're going to get the same kind of thing where it kind of falls in. All right, so that's pretty interesting. Next time what we'll take a look at is what happens when we use a driving force that's not a power law. So we'll try to go beyond the power law structure that we've had so far.